These days, hardly a day goes by without hearing about the latest advancements in AI hardware. Ever wondered how these technologies work? In this short video, we break down the complexities of AI hardware and explain its crucial features. Let's start with a simple deep neural network or DNN, where the number of parameters or weights typically characterizes its size and complexity. A rich training database measured in tokens fuels our model, providing the data it needs to learn and refine its predictions. To train a neural network, we rely on a GPU and high bandwidth memory or HBM. The GPU loads our model's parameters and training data directly into the HBM, whose capacity is measured in gigabytes. The GPU performs a massive number of calculations as training begins. Its processing power, expressed in flops, indicates how quickly it handles complex mathematical tasks. A flop or floating point operation is a calculation involving real numbers with decimal points, such as addition, subtraction, multiplication, or division. The higher the number of flops per second the GPU can perform, the more powerful the GPU is. During processing, the GPU exchanges substantial data with the memory. The memory bandwidth, measured in bits per second, shows the speed at which data flows between the GPU and memory. For AI processing, this feature is crucial, as insufficient memory bandwidth can create a bottleneck. That's why we use HBM instead of traditional memory. As deep neural networks grow into larger structures, we witness the immense scale of models and the pressing need for more processing power. For perspective, while the number of parameters in this simple model is in the hundreds, the large language model GPT-3 has 175 billion parameters, and its successor GPT-4 has a staggering 1.75 trillion parameters. Today's massive models and training data no longer fit within the constraints of a single GPU and HBM configuration. To accommodate this scale, we need to increase computing power and utilize parallel processing. Therefore, we equip GPUs with additional HBM modules. As the demand for processing power skyrockets, newer and more powerful GPUs are developed, featuring larger sizes and more transistors packed onto a single silicon chip. To scale up further, we replicate this structure to form clusters of multiple GPU HBM stacks. To efficiently use these massive computing clusters, parallel processing is employed. In data parallelism, the entire model is loaded onto each GPU, while the training database is divided into different subsets, with each subset processed by a different GPU. Next, we explore two methods of model parallelism. In pipeline parallelism, the entire training dataset is available to all GPUs, while the model itself is split into multiple sequential parts, each loaded onto a separate GPU. In tensor model parallelism, we divide parallel subsections of the model across multiple GPUs, ensuring each GPU is responsible for a portion of the neural network's layers. To meet the growing demand for processing power, we need more GPUs to scale up our computing capacity. However, building an efficient data center isn't as straightforward as placing GPUs side by side. Let's take a closer look. We start with a PCB, or printed circuit board, and install two GPUs on it. This board forms a powerful computing module. To further increase our processing power, we can stack up these boards in a rack. But that's not all. To ensure seamless data exchange and processing, additional circuitry is needed. For example, two different PCBs representing these components are included in the system, enabling reliable communication between GPUs. In a real data center, many racks or cabinets are lined up side by side, forming a seamless network of computational power and high-bandwidth connectivity. This architecture allows us to scale up processing capacity to meet the demands of even the largest AI models. Hardware and microchips play an essential role in the rapid advancements and evolution of artificial intelligence. These innovations are not only increasing computational power, but also making AI more efficient and accessible, empowering all of us to push the boundaries of what's possible. Thank you for watching, and I hope you enjoyed this video. Be sure to check out our other educational videos for more insights into the fascinating world of AI and hardware.